Okay, Assalamualaikum warahmatullahi wabarakatuh. So let's continue our chapter. So in the previous video, you learn about DC analysis. Where in your DC analysis we have direct approach, right? But it's difficult to solve. So we go to the mathematical model. We have number one is ideal model. What does that mean by ideal model? You're going to replace your diode with a short circuit. So means here your V gamma is equal to 0. Now we move to the second model. So second model we call here piecewise linear model 1. So the name here is PLM1. So you're going to replace your diode here at the volt bias with what we call V gamma. What is V gamma here? V gamma here is the VBI in the previous chapter. Minimum energy required to pass the barrier, or we call turn on voltage of a diode. Why we need to do DC analysis? Because diode is an active device. We need to make sure the diode turn on. Okay, so let's see the second model, that is piecewise linear model 1. So there are two conditions. So your original circuit is like this. So here is your diode and here is your input. So it can be either plus minus or minus plus. So during the reverse bias, so what will happen during reverse bias? You're going to start here minus and plus. So what will happen to the diode? So in order for the diode to turn on, the voltage here must be plus and minus, because why? The diode only allow the current to flow in one direction. So if we apply here, let's say your voltage here, this area is minus, right? So minus plus, what will happen to the diode? The diode will be off and then it will be open circuit. So that's what it shows here, open circuit. So during the reverse bias, when the diode will become open circuit, what will happen to the current? There will be no current, so I will be equal to 0. So this is what represented by this area. So this is what we call reverse bias. So in this condition, so we have what we call V gamma. So what is V gamma here? V gamma here means the turn on voltage. So you need to pass minimum V gamma in order for the diode to turn on. So in this case, if the voltage is still less than V gamma, the diode will be still off. So here will be current will be 0. So here it will still be reverse bias. That's why the condition at the reverse bias is not only less than 0 here, it must be less than V gamma. Okay, let's see what will happen when your Vs start to become more than V gamma, means it overcome the turn on voltage. Your diode will be on. Okay, so when the diode is on, you need to replace your diode with what we call a voltage source called V gamma. So at first means if we redraw the circuit again, so this is your sine wave, this is your diode. Now instead minus plus at the reverse bias, now here become plus minus. So plus minus means it goes to plus, right? So the diode will become on. So when in the piecewise linear model 1, when it is on, you're going to replace your diode with what we call V gamma. So that's where this area is called forward bias. So remember, when forward bias, you apply here plus minus. Reverse bias, you apply here minus plus. So there are two conditions here. So for the piecewise linear model 1, during the reverse bias, as long as it is still less than V gamma, the diode will be off. Off means what? Open circuit. But when it is become more than V gamma, so this condition when your Vs is more than V gamma, what will happen? The diode will be on. And then you're going to replace your diode with what we call V gamma. So it is represented by the battery voltage. This is what we call V gamma, or we can call this one turn on voltage. Okay, so let's see one example. Again, the same circuit with the ideal model. The question 1, VD and ID. Using which model? Which means constant voltage model. So why it mentioned here constant? Mean in this question it gives the value of V gamma. So when you want to solve this question, always remember what happened during reverse bias. what will happen during forward bias. So during reverse bias, you're going to put here minus plus. So what will be happen to the diode? The diode will be off, right? What will be off? Open circuit. So you have no current at the reverse bias. So what is the condition for this reverse bias? When your Vs here is less than V gamma. So let's say I apply here 0.5 volt. So will the diode turn on or off? Because it is less than 0.65, so it will be, the diode will be off, and then the current will be 0. During forward bias, what will happen? So let's say here it will be plus, here will be minus. Then the diode will be on. So you need to replace your diode with what we call V gamma for model 1. So let's say here I redraw again. So here become 5. You have a resistor. So the diode will be on, and then you're going to replace with V gamma. So what you need to do now is you need to find the current. So you can use Ohm's law. So means I equal V over R, or you can use KVL. So what is the KVL here? Minus 5 plus R I D. What is the I here? I D plus V gamma equal to 0. And then you can get your ID equal 5 minus V gamma divided by R. So it will be the same like here. So remember to put the unit, the current will be 2.175. Okay, question number 2. We already know the current. How you can get the voltage? So where is the voltage here? Voltage of what? Not voltage of the whole circuit. It is actually voltage of the diode. So at first here you have a diode, right? So your VD here will be V gamma straight. VD equal to V gamma. So how you calculate power dissipation again for the diode? VD multiplied by ID, and then you can get the power dissipation. Okay, so now let's move to the last model. So just now, your ideal model, you replace your diode with a short circuit, right? Means here is V gamma equal to 0. Second model, PLM model 1, you replace the diode with V gamma. What is the third model? We call this one PLM2. PLM2. So where you're going to replace your diode with V gamma and RF. Okay. So let's see again the same explanation happens here. With reverse bias, you apply here minus plus. So means as long as it is less than V gamma, it will not enough to turn on the diode, right? So it will become open circuit, and your current here will be 0. So this is what you call reverse bias. At the forward bias, where you start to apply here plus and minus, your diode, so at first there is a diode in between here. You're going to replace your diode with what we call RF and V gamma. Okay, so in model 2 only V gamma. So model 3 become more accurate where you're going to replace your diode with V gamma and RF. So this is only applied when the condition where Vs is more than V gamma, where it will become forward bias. So since there is RF here, so there is a slope. So this slope, what we call R equal V over I, right? So this slope, what we call RF. So this is what we call piecewise linear model 2. So in this condition, where when Vs is less than V gamma, it will become open circuit. When it is more than V gamma, you're going to replace your diode with what we call one voltage source, that is V gamma, and in series with RF. In series with RF. So the same question with the previous model. So what is the changes here is only this word, piecewise linear model, and you are given V gamma, and you also will be given RF. So once there is a RF here, you know this one is piecewise linear model 2, where you're going to replace your diode with what we call V gamma in series with RF. Okay, so again, the same circuit. During reverse bias, there will be no current, right? So we don't need to do that. During forward bias, when you're going to apply a plus, minus, correct? Your diode is your supply here is 5. So means your Vs here is more than V gamma. So what you're going to replace here is you're going to replace your diode with what we call V gamma and RF. So let's do the KVL equation here. So KVL says here, so minus Vs plus R ID, this is the current is diode current, plus V gamma plus RF ID will be equal to 0. So how you can get your ID? Is actually Vs minus V gamma divided by R plus RF. So this will be the equation for the diode current. Same here. And you can get your diode current. Again, this question will ask diode voltage and diode current. So what is the diode voltage? So for your diode voltage, this is the diode, right? So you're going to replace this with these two elements. So what is the voltage drop at the diode voltage? So VD is equal to V gamma plus ID RF. So the same here. Okay. So the last question, how you can get the power dissipation, not for the whole circuit, power dissipation of the diode. So you just multiply VD and ID. Okay, so as the summary for your DC analysis. So this is a DC analysis of your diode. So we have 3 models. The first one is ideal model. Second one is PLM, and then 1 and 2. So in your ideal model, you're going to replace your diode with a short circuit. Here, replace your diode with a voltage source that is called V gamma. Here, you're going to replace your diode with V gamma in series with your RF. Okay. So from the same circuit you have analyzed before these 3 models. So as we can see, the current value, voltage value, and the power dissipation value, this PLM model 2 is the most accurate one, which this result is almost near to the direct approach. So we can see that this piecewise linear model 2 is the most accurate compared to the other 2 models, because in this method we're doing we do some assumption, right? So the most accurate one is piecewise linear model 2. So how are you going to tackle the question? So you see what is the value given in the question. So it only gave V gamma and RF, so you know this one is PLM2. If only V gamma, then this is PLM1. And when V gamma is equal to 0, you know that this is ideal model. Okay, so if you have any question, let me know. So we move to the graphical approach for the next video. Assalamualaikum warahmatullahi wabarakatuh.